Super. So there was a question before we started the recording, which was, we spent a lot of time on 2D rotations. We're doing 3D rotations in the homework. Are we going to do translation? And the answer is, first of all, you've already done them. I'm good. I think it's the iPad that's muted. Thank you. Thank you. Let me just double check. Oops, that I've disconnected the audio because sometimes there can be, yeah, there can be some feedback. Yeah, so you've already done translations. In fact, we did them when we did the e to the I px's, e to the plus minus I px's, and we did. Yes. And in a sense, in the same way that, because SO2 is abelian, was therefore, in some sense, trivial, all the representations were one-dimensional. The e to the I px's, or e to the I pa's, let's call it, the translation group is abelian in n dimensions. So all of its unitary irreducible representations are again one-dimensional. So it's actually quite trivial in some sense. Then you asked about the Poincare group, which is an excellent question, because if we assume that the symmetry group for that exists around us, that determines physics, is the Poincare group, i.e. that we live in a world of special relativity as a basic assumption, then what we would want to do is we would want to classify the unitary irreducible representations of the Poincare group, which would tell us what possible particles we could have to describe our world, and would tell us how those particle states transform under Poincare transformations, translations in time and space, rotations in time, and rotations in time and space with boosts. That's beyond the purview of this course. That would be more of what would be done in a quantum field theory context. But that's an extremely interesting question. And the technique that we're using to determine all of the unitary irreducible representations of the rotation group, the theorem of highest weights, that will not be helpful for the Poincare group, because the theorem of highest weight is really only going to be helpful for you for compact groups, and the Poincare group is not compact. What one does for the Poincare group is rather the method of induced representations, which is a whole other kettle of fish, which again, you can learn at some point, and I encourage you to learn at some point because it's super interesting. Good. Yeah.
I have a question about the last lecture. Just at the end, we did something else.
Yeah. So let's hold off on that. My intention is to give, as it says up there, a big picture overview, and then to go through fairly quickly, but please stop me if there are places, everything from the start of the Lie algebra section last time, which I feel was rushed, and then some people had to leave. And just to confirm, so people, is there or is there not a hard cutoff for people at some number of minutes before 11 a.m. to make it to another class? Today. So to the last one there was, but today not. Okay, I don't intend to go long. I didn't intend to go long last time. I'm sorry that I did. I wanted to get to a stopping point. We'll see where we get today. It all depends on you in a good way. If you ask questions and we take time, then it takes a little bit longer, and I'm okay with that. I hope you're okay with that. That's, I think, where the real learning happens, when we have that back and forth. Cool. Any further questions before we get the ball rolling? I don't see anything, so let's do that. All right. So big picture. We're working through in the homework in complete detail all of the unitary irreducible representations of SO3. Why is that we want to do that? And the reason is basically what we talked about with respect to the Poincare group, that classifying the unitary irreducible representations of our symmetry group, well, actually, let's take a step back. Yeah, we know that symmetry transformations exist in the world. We would like to describe the world in terms of physics, in terms of math. And in this course, we assume that the world is described by the postulates of quantum mechanics. So we would thus like to be able to describe a general symmetry transformation in a quantum mechanical framework. Hilbert's fifth problem tells us that a symmetry transformation is a Lie group. And so we're thus looking for some map between Lie group elements into complex vector spaces, because quantum mechanics lives in a complex vector space. That mathematically, that map, along with the vector space, is what's known as a representation. Just a technical term, which we've worked through in some detail in terms of the definition of it. We said that the fundamental building blocks of a representation are the irreducible representations. Just like the integers are the fundamental building blocks of the rational numbers. You'd like to understand the building blocks so that you can build up more complicated objects. We said that Wigner's theorem tells us that the representations are either linear and unitary or antilinear and anti-unitary. We're going to, in this course, consider only groups that are continuously connected to the identity elements. And therefore, we'll only need to consider unitary representations rather than the anti-linear, anti-unitary representations, which is a relief because they're a pain. As much as this is difficult, it gets even worse. Okay. And so, as mentioned, these unitary irreducible representations will tell us the permitted quantum states consistent with a particular symmetry transformation. So we can think about various symmetry transformations, such as translation, spatial translations, such as rotation, such as Poincare transformations. Okay, so that's our goal. We want to classify these unitary irreducible representations. And we said that that is a difficult task, to go directly from the group to the group of general linear invertible transformations on a vector space. And that rather the path that we're going to take, instead of going from G to GLV via some representation map, is we're rather going to go up to the Lie algebra of our group, for which we have a map from the Lie algebra to the group, the exponential map. And we're going to look at the representations of those generators going from the Lie algebra of the Lie group to the Lie algebra associated with the group of linear transformations on the complex vector space, where again, there's a connection via the exponential map. Good. And we're going to look at compact groups, SO2, SO3. We spent a lot of time on SO3. So we're going to utilize what's known as the theorem of highest weight. The Lie group that we have is a real Lie group because it's associated with a symmetry transformation in the real world, which means there are real world parameters, angles, axes, distances, real numbers. So this is a real Lie group. So this would be a real Lie algebra. The tangent space of a real manifold is a real vector space. We're going to do something that seems like we're making life harder. We're going to complexify our algebra. We're going to allow for complex linear combinations of the vectors. But this is exactly like what happens with the real numbers and complexifying the real numbers. That, for example, integrals over the real numbers can be made much simpler if we allow a generalization of the real numbers to the complex numbers. Then we can do contour integration. Or maybe a more simple example, if you'd like to find the square root of -1, you're unable to do that in the real numbers, and complexifying allows you to have a simpler algebra. And the same thing is true within this group theory. So we're going to complexify our real group into a complex, allowing for complex linear combinations. And that'll allow us to find raising and lowering operators. We like raising and lowering operators. It allows us to determine non-trivial information about our group based purely on algebraic properties, the commutators. And this will allow us to determine the possible irreducible representations. Then we're going to lean on some math that I'm just going to state for you. And the math says that the irreducible representations of a real Lie algebra are in one-to-one correspondence with the irreducible representations, the complexification of the real algebra, right? So we started with saying we want the representations of the real Lie group. That's hard, so we go up to the real Lie algebra. But finding the representations of the real Lie algebra is also hard. So what we're going to do is we're going to complexify that Lie algebra. And that is not too bad. We can find the irreducible representation of the complex Lie algebra. But gosh, we're a long way away from our real Lie group. How do we know that what we've done is of any use for us? And the point is that once we have found these complex representations of the complex Lie group, we're assured that those representations are the same representations of the real Lie algebra. And therefore, those are the representations of the real Lie group, this pi that we're looking for. Yes. 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 And in a non-condescending way, you are absolutely welcome to go. I can point you in the direction of certain resources where all of these things are proved in detail. But it's, yeah, it's sick books. Yeah, yeah. Okay. Good. So that's the first chunk. Let me pause there for any conceptual questions. And if there are no conceptual questions, then there's this additional degree of difficulty, which we've talked about several times, but there's a lot to keep in your brain all at once, so I'm going to say it again. And that's that quantum mechanics is insensitive to overall phases. And so as a result, we are forced to consider not just ordinary representations, but also projective representations. And another theorem tells us that groups that are simply connected and whose algebras don't have any central charges, but we'll not worry about that too much. If the group itself is simply connected, then the representations are all ordinary. And further, that all ordinary and projective representations of some group G descend from all of the ordinary representations of the universal cover of the group G twiddle. And we talked about it, we'll talk about it again today. I believe I talked to all of you yesterday in the tutorial what simply connected means and what universal cover means. So simply connected means that every single closed path inside of your manifold can be continuously contracted to a point. Yeah. So for example, if you're in three-dimensional space, that's simply connected. Any Rn is in fact simply connected. If you're on the donut, if you're on the surface of a donut, if you're just on the surface of sort of like one side of the donut, that those closed curves can be contracted to a point. But if you go around the donut, one way or the other, then that curve, which is closed, cannot be continuously contracted to a point. And part of your homework is to convince yourself that the group SO3 is not simply connected. And so we will anticipate that there are projective representations of SO3, which we must take into account because we're doing quantum mechanics. Okay. And then there's the universal cover. The universal cover of a group is the group which has the same Lie algebra as the original group and is simply connected. And what we will say is, in fact, basically, in practice, not basically, in practice, what you end up doing is instead of working with the unitary irreducible representations of the group of interest, you rather end up working with the unitary irreducible representations of the universal cover. And so what you're really going to do is you're going to prove to yourselves that SU2 is the universal cover of SO3. And then you're going to find the unitary irreducible representations of SU2 and use those whenever you are trying to do anything in terms of rotations. And you're guaranteed by math that that procedure is okay. For which I'm anticipating giving you some additional optional problems in the next homework set to really tie everything into a bow. Okay, so that's the big picture. Are there any questions on the big picture? I've now said, I feel like I've said the big picture several times. Do you feel like it's sinking in or is it still okay? Yeah, good. And as I said, it's a lot of stuff to keep in your head at one time. So please ask questions as we go along. All right, great. So we want to compute all these UIRs, and we said that to do so, we want to compute the UIRs of the Lie algebra. So what is a Lie algebra? And the point is that locally, we can learn everything about a Lie group by expanding infinitesimally about the identity element. So we should think about that systematically. So we're thinking about some general symmetry transformation. So it depends on some number of real parameters. And we're going to think about a connected Lie group. So we're going to not consider discrete transformations like reflections or time reversals. And every element in the group is connected to the identity by a path fully within the group. So there's a difference between connectedness and simply connectedness, right? I could think about, for example, a chunk of R3 and a disconnected chunk of R3, where there are certain areas of R3 that I cannot, of these manifold, that cannot get to each other. So it is not connected, but it is simply connected, because any closed path within any of these chunks can be continuously contracted to a point. Good. So this is simply connected but not connected. I can also think about connected but not simply connected. SO3 is an example of a manifold that is connected but not simply connected. Or the two torus is again connected but not simply connected. So the only thing that I'm going to require is that this Lie group, this group of transformations, is connected to the identity. And a lack of simply connectedness is going to lead us to projective representations. Okay, because this is a group, there is a group multiplication law. And what does that mean? It means that if there's some transformation based on some parameters theta c, followed by some other transformation by parameters theta bar b, then this has to be a single transformation, which is some function of the parameters that give the first two transformations. It's very general. So it's just, I just have that there are some n functions f that are real, because this group is a real group. And it's a function of n plus n, which is 2n parameters. Now, we would like to understand some properties of this f function, general properties. One property we could think about is we could imagine having the first transformation be the identity transformation. Nothing happens. So then our parameters are all 0, or it's the identity equivalently. All right. So that tells me then, I guess, let's write this actually rather as the bar. Theta bar b is 0. Then we have that the transformation by parameters theta a is a transformation by theta a followed by the identity. Sorry, I got it swapped around. Fine. And so this must be by the group multiplication law, fa of theta c followed by 0. But this fa has to be equal to theta a. Right, so I'm doing a transformation by theta a, which is a transformation of theta a followed by nothing. By the group multiplication law, this must be equal to some overall transformation of which is given by these functions of the theta c and theta b parameters. In this case, the theta b parameters are just the identity, it's just 0. So what does it tell me? It tells me this theta a has to be equal to the fa. You're looking confused. Okay, good, good. And the same thing in terms of if I do nothing, then I do a transformation, then my function is just the theta bars. So that tells me then that an expansion of this f, and everything we're doing is using calculus over and over again, starting near the identity. So not everything, but a lot of what we're doing is that. So we're always in our mind, we're thinking about Taylor expansions and keeping track of what orders these small parameters are. So if I do a Taylor expansion of this f, it's 0 plus linear in the thetas, linear in the theta bars. And then I can look at the quadratic part. So I have a quadratic part in thetas, the quadratic part in the theta bars, and then one part that is a mixture of the theta and theta bars, and then plus higher orders in theta cubed, which I'm not going to worry about. All right, all of these f's are real numbers. These f's are real numbers. But we just said that if I put 0 in for the the theta bars, then I get exactly theta A. No higher orders. It's exactly theta A. So what happens if I do that? So if I put in theta B0, then this goes away, and then this goes away, but I have some extra junk lying around. Unless this is identically 0.
Sorry, can you repeat that?
Yeah, so this is true in general. This is some general expansion using the fact that I have nothing at 0th order, and then I just have the leading order pieces. These are the quadratic pieces. Now, let's put in 0 for the theta bar B. That kills this term, and that kills this term. So but I do have this term remaining. This term, oops, not that term. This term also goes away. But I know that if I put 0 in for theta B, my FA is exactly equal to theta A. I put in 0 for theta B, goes away, goes away, goes away. I have this, which is this, but I also have this extra stuff. Unless this is identically 0, this coefficient. Good. I ran out of letters, basically. So I'm going to, when I did this the last time, I just did, whoops. When I did this the last time, I left off these terms because I knew that they were 0, but I felt like it'd be worth going through explicitly the argument for why they are 0. So it's getting a little messy with the bookkeeping. So I have an FABC with the theta bar BC. So the B's and C's are contracted. And I have the A left uncontracted associated with the A index on the left. And there's this F. So then these F's also have ABCs for the same reason. I somehow either dropped or erased and put back the A there. But I need to distinguish this F from this F from this F. So I did that in the best way I could think of, which was to have sort of a parenthetical theta and parenthetical theta bar. I also thought about like an overbar, a double. I know it just like starts to run out of. I mean, called it as a G and an 8. I don't know. So the point. Okay, so that answers your question. Good. So the point is, by 2, I can argue that this F is identically 0. And by a similar argument, I can argue that that F is identically 0. And so we must have good. So we must have that this FA expands like so. There's one other nice property. We know that if we have a translation symmetry transformation by some parameters theta A, and we have the same symmetry transformation, but by the opposite of those parameters. So I rotate by 90 degrees to the left, then I rotate by 90 degrees to the right. I've undone my symmetry transformation. So I get back to the identity. So that tells me that if I say, if my theta bar A is minus theta A, this part will cancel, but then this part is not necessarily 0. Unless my F is antisymmetric in the BC indices. Okay. Good, because if this is antisymmetric in the BC indices, if this is the same as this up to an overall sign, this is symmetric, this is antisymmetric, and I automatically get 0. All right, good. So this is important. We have derived the expansion of this F function, the generic, we've found a very strong set of restrictions on the possible multiplication laws of our symmetry transformations up to order in the parameter space cube, parameters cube. That it's linear in the first argument, linear in the second argument, only quadratic in the mixed arguments, where the function that tells us about that mixing is antisymmetric in the lower cases. Any questions on that? Great. So now what we want to do is we want to consider the unitary representation of our group. Since it's a Lie group, we can perform calculus and expand the identity. So in general, we have some symmetry transformation, and we have some map that is taking a generic symmetry transformation into the set of operators that act on a vector space. And by Wigner's theorem, they are necessarily unitary. So I got a hat that tells me it's an operator. I have a U that tells me it's unitary. By simple calculus, I know that this operator is going to, if I expand for small values of the parameter, I'm going to get the identity continuously connected to the identity. So I have to have the identity in there. Then I have some linear term, some term linear in the parameters with some operatorness that I'm just going to give a name, which I'll call TA hat. And for reasons that will become apparent, I pull out an I. Then I go out to second order. So I get parameters twice, and I have some operatorness that I'm just going to name T hat AB with a factor of half because this is it's going to be an exponential. So it's going to make sense. There's a half, and then higher orders. Okay. Since this operator is unitary, or the map is unitary, U dagger equals U inverse. That tells me that this thing that tells me about the operatorness, the linear order operatorness, this has to be Hermitian. You can see it from the minus I goes to minus I. Maybe I'll have you do that explicitly in homework. It'll be like a two-liner. Oh, good job. All right, good. So it's Hermitian. And what does that mean? It means that the generator of the group is Hermitian and thus is potentially observable in quantum mechanics. Right? Remember that if you have a Hermitian operator, then its eigenvalues are real, its spectrum is real, and that its eigenkets form a complete basis for the space. So it satisfies all the properties that we would want for an operator, for something that represents an observable in the real world. So if Hermitian, then possible, so in fact, if generator of symmetry transformation, then potential observable. But interestingly enough, so Weinberg, who's, nobody knew any more than this, Weinberg said that he was unaware of any observable in the real world that was not the generator of a symmetry transformation. So it seems like this is an if and only if statement in terms of the things that can be measured. That certainly if it's a generator of symmetry transformation, it can be measured, but it seems like anything that can be measured is in fact the generator of a symmetry transformation. Okay, good. So if we come up here, these thetas are just real numbers. Real numbers commute. So this object is symmetric in the AD indices. And so that tells me that this T hat AB is also symmetric in the AB indices. Here. Okay, good. Questions? All right. So suppose that these U's form an ordinary as opposed to projective representation. What does it mean that's an ordinary representation? It means that the map preserves the group multiplication property. What is the group multiplication property? We just defined it up above. We said that if I have a transformation by theta C followed by a transformation by theta bar B, then I have a single transformation by FA that's a function of the theta bar B and theta C. So if I have an ordinary representation of this group, then I just put U hats everywhere in front of these things. If it's projective, then I would get some additional phase. I have the ability to put a phase there. We'll cover that later. All right. So I'm assuming that my U's form an ordinary representation. What are we going to do? The same thing that we do every night, Pinky. We're going to expand around the identity. Thank you for a couple people for smiling who are aware of things that happened in the 1990s. So let's expand both sides out to order theta cubed and see what happens. Let's first expand this object. And we know what the expansion of our unitary operator is. It's given here. So it's 1 plus I parameters and then our T hat A, and then plus a half, 2 parameters, and then theta hat AB, and then order theta cubed. So I'm only going to do that. all I'm doing is precisely expanding that here. So I have the theta bar b. So I have the 1 plus I theta bar, right? A, TA, A's are dummy indices. And then theta bar A, theta bar B, TAB with a half. I do the same thing with the theta C. I get the same thing, except these parameters are now thetas, not the theta bars. And if I multiply this out, so I take this piece and bring that here. I take this piece and I bring that here. And I just multiply out order by order. So I have 1 times 1 gives me 1. I have I theta bar A TA times 1 plus I theta A TA times 1. That gives me this piece here. Now I have the second order piece. I can get the second order piece in 2 different ways. I can get the second order piece with the 2 linear pieces. So that's here. Or I can get a second order piece from this second order piece times 1 plus this second order piece times 1. And that's these 2 pieces. Good. All right. That's the left-hand side of this expression. Let's now compare to the right-hand side of that expression. Now what I need to do is I need to do the exact same kind of expansion as I had here, but instead of the theta bars, I'm going to get the FAs. And the FAs, we said, after our investigation up above, are given here. There's a linear in the theta, a linear in theta bar, and then a quadratic. I'm expanding systematically to order theta cubed. So what does that mean? It means that I insert for my FA the expression up to order theta cubed. So this is correct up to order theta cubed. I have the 1 plus the first expansion of the U, which gives me the TA, and then the FA up to order theta cubed. And then I have the second order expansion of the U, which gives me the TAB, and then the FA squared up to only order theta cubed, which is going to be the linear term squared. I got 1 nod. Everybody okay with that? Good. Now I want to compare the left-hand side, which is correct up to order theta cubed, with the right-hand side, which is again correct up to order theta cubed. I demand that to order theta to the 0, I get the same thing, and I do. 1 equals 1. I demand that to linear order in the thetas, I get the same thing. And in fact, I do. I get the TA here and the TA here. So I'm sort of doing things to the green, the blue, the red, the red. All right. Now I need to further get the same thing to order theta bar squared. So I get a theta bar A, theta bar B, TAB with a half. And I look over to this term over here, and I see, comparing purple to purple, theta bar A, theta bar B, a half TAB, they are the same. Very good. Same thing for the orange for the quadratic in thetas. So all of this has been boring and uncontroversial, straightforward. Now we get something interesting. We get something interesting when we compare the mixed quadratic terms. So on the left-hand side, I have a minus theta bar A, theta B, TA hat, TB hat. And on the right-hand side, I have an I, FABC, theta bar B, theta C, TA hat. Plus, I have a theta bar A, theta B, TAB hat. And a theta A, theta bar B, TAB hat. On the right-hand side, this TAB, we argued, is symmetric in AB. So I can change the dummy indices here, AB, AB, I can swap them. So I get rid of the half. And so what I find is that minus TAB, T hat A, T hat B here, dropping the theta bar A, theta B, is going to be equal to TAB hat here. And then I have to do a little bit of index dancing in order to get my theta bar B to a theta bar A and my theta C to a theta B. So I need to change this dummy index B to an A, this dummy index C to a B and change this to some other letter, call it C, and I get the I. So I get an IFCAB TC. Got a nod there. Everybody's on board. All right, excellent. So this does something super interesting. This is actually giving me an explicit form for the TAB hat in terms of the linear terms and these Fs. So I'm able to construct explicitly the quadratic term from the linear term simply by self-consistency. And this is actually a fully general procedure. I'm able to completely reconstruct all higher order TABC hat, TABCD hat, so on and so forth, in terms of all the lower order pieces. It boils all the way down to understanding the linear and these Fs. That's the first statement. The second statement is that this is very interesting because I know that the TAB is symmetric in the ABs. So I can just relabel everything. So I can call this a B and a BA, and then a BA. And then I can subtract those two equations, right? So I relabeled the B's and A's, and I did that here. Call this equation 14. And I can simply subtract equation 13 from equation 14. This is a true statement. This is a true statement. I can subtract two true statements. When I do that, my TABs will cancel because they're symmetric in the lower indices. The left-hand side will become TATB minus TBTA. And then the right-hand side will become IFCBA minus IFCAB. And you might think, oh, I've killed everything, but I haven't, because remember that these Fs are anti-symmetric in their lower indices. So let me just rename this something else. And what I find then is this left-hand side, which we see all the time, I will call it a thing. I will call it a commutator. Or in the context of what we're doing here, I'll call it a Lie bracket. And so the Lie bracket is given by ICCAB TC. So these C's are known as structure constants. And as I mentioned, locally, they fully generate the Lie group in the neighborhood of the identity. And so our self-consistency relation tells us that everything we need to know about the group is determined by these structure constants. Yeah. Yes, precisely. Local to the identity. So global properties. So if your group, and I think I mentioned this. So if your group is simply connected, not only do the structure constants tell you everything you need to know locally about the identity, they tell you everything. But if your group has non-trivial topological properties, global topological properties, then you have to think more carefully about how to describe all of the elements of the group.
Why is it useful?
So I would say in the context of what we're doing here, it's it's interesting insofar as we're going to use the expansion of the group around the identity in order to construct our unitary irreducible representations. And so we're going to be using the Lie algebra structure of the group in order to construct those unitary irreducible representations. So in our context, I would say that's our main reason for considering these things. But I would say that more generally, it's you would, as a physicist, I would think, as a physicist, I try to understand the world in some sense, sort of the least number of equations. Like I want to sort of rational reductionist way of viewing the world. Like what is classical mechanics? It's a variation of the action is zero. And it's like, oh, okay, I don't need all of these ad hoc rules. I'm not a biologist naming a bunch of things. Like it all comes from a single first principle. And I would say from the mathematical point of view, the first principle of Lie groups is just the structure constants of the Lie algebra. So I think in that sense, it's a very nice way to think about groups. And then, as mentioned, because the structure constants tell us everything locally that we want to know about the group with the identity, we're able to very easily figure out whether groups that a priori we would superficially think are totally unrelated are in fact the same, at least locally to the identity. As an example, SO3 and SU2. I don't quite understand your question. So in your homework problem, in your homework set, you work out the commutation relations of, say, the generators of rotations, and those are the structure constants. Could you close the door, please? And I hesitate. I hesitate to say that because you're like huge smiles. You're like you're super excited. Good. Super duper duper. Okay. Any further questions? Good. All right. So what I call, and I'm following, as I think I've mentioned, to a large extent, Weinberg's notation. These CABs are often written as Fs. So just there's a factor of 2 difference. So just beware. Okay, so we've started throwing around terms like Lie algebras. We haven't actually defined what an algebra is. So I'd like to briefly do that. So an algebra over a field K is a vector space over K with a bilinear map. For us, the field is going to, well, I was about to say the field is generally going to be complex numbers, but that's not true. Because our algebras actually start off as real algebras. So the field that we're going to start with is the real numbers, and then we're going to complexify. Okay, in order to distinguish between the groups and the algebras, we're going to follow a fairly standard notation where we're going to write our algebras in what's known as fractal or Gothic font. It's kind of a pain. I know, it's kind of cool, but it's kind of a pain. So thank the Germans. All right, just to sort of note something that I thought about, maybe a complication for you also. So you are used to having vector spaces with a norm, which are Hilbert spaces. And a norm is a map which takes 2 vectors and spits out something else, but that something else it spits out is a scalar. And the bilinear map, and the norm is a bilinear map. So you're like, oh, a vector space with a norm is an algebra. No. Because the norm takes 2 vectors and gives you a scalar, rather than in an algebra where you have 2 vectors that give you another vector. All right, good. I think I need to, no, I'm just going to say this stuff. So at some point I'm going to start writing because we're getting into new territory, but I would say this stuff is, we can skim over. It's sort of more for your character than necessary, that is 100% necessary for the course. So some examples of algebras, the real vector space of 3 vectors equipped with a cross product. Note that the cross product is a non-associative algebra, that order matters, right? Also, the complex numbers equipped with the usual complex multiplication, that's an algebra. Less standard for me are the quaternions and the octonions. Whenever I see those, my eyes glaze over, but they are algebras. All right, good. Now, okay, so this is an algebra. Let's define a Lie algebra. So Lie algebra is an algebra whose bilinear is antisymmetric and satisfies the Jacobi identity. So this is a stronger restriction. So all Lie algebras will be algebras, but not all algebras are Lie algebras. Okay. For your, again, character building, these are words and sort of concepts that I would like you to have been introduced to, but that I certainly don't expect you to understand in detail. And you may not even understand superficially, but I want to get the words in your brain, right? So from differential geometry, which is calculus on general spaces that might be curved, if we think about it in that context, these TAs act as vectors in the tangent space. Well, yeah, so it's sort of important. I take that statement back. It's sort of important to sort of understand this. So the TAs act as vectors in the manifold of the identity. And the commutator here, the commutator, which I said is also known as a Lie bracket, is a bilinear map from the set of TAs to themselves. And so this tells us that the set of TAs equipped with the Lie bracket forms an algebra, and therefore every continuous Lie group G has an associated Lie algebra G. This is something that probably you know, or you've sort of been told, or sort of implicitly understood. But now I would like to believe that I have, at least in principle, so you may not understand, differential geometry, you may not have that course, you may not have tangent spaces, but I would like to think that you can believe these statements. And therefore, we conclude that every continuous Lie group G has an associated Lie algebra. Right. As mentioned, in a finite neighborhood of the identity, the Lie group is completely determined by the Lie algebra, and vice versa, which is done by the exponential map. And okay, so this is the part where especially it's just for seeding your brain with ideas. The fact that you can completely determine the local group structure, Lie group structure from the structure constants, is exactly equivalent for the need for only the curvature tensor to give the local structure of a manifold. So there's a deep connection between the Riemann curvature tensor and the Lie bracket. So yeah, there's a lot of really cool connections in the math that's going on here between topology, algebraic topology, group theory, representation theory, and differential geometry. It's all in the mix in a very deep and satisfying and really cool way, which I encourage you to investigate via Wikipedia and math.stack exchange, et cetera, et cetera. All right, good. Any questions before I continue? And where is my cursor gone? There it is. You're welcome. So from this paragraph, I don't expect you to know differential geometry. I don't expect you to know tangent spaces. I don't expect you to know manifolds in any depth. We can talk a little bit about the idea of what a vector space is, which we want to define in a coordinate independent way. And the way that people do that is they say, okay, I've got some manifold, I consider some point, I think about all possible curves within the manifold that go through that point. Curves are objects that are parameterized by a single parameter. So I can think about the derivative of that curve, of any of those curves with respect to that one parameter. And each of those tangent vectors will be a vector. And if I think about all of those tangent vectors, that forms a vector space. And that's the space of vectors that lives at that point that I can think about in terms of this manifold. And so in the way that we have been doing this expansion of our map around the identity, we can think about these generators as the basis vectors of this vector space. And then what we would like to understand is if I take one of these vectors and I parallel transport it around a little square, do I end up with the same vector or something different, slightly different? And if it's slightly different in the differential geometry context, that means that there's some curvature. And in the group theory context, it means that the commutator is non-zero, I have a non-commutative group. Okay, good. Other questions? Yes.
The last sentence on the screen, what is the word of
Neighborhood.
Okay.
Welcome. Good. You can see I get a little bit tired of groups, and so I say GP neighborhood.
I'm familiar with that.
Good. Other questions? Great. All right. So let me start a new notebook so that it slows me down to write things. I already did that. Okay, so here it is. I was already prepared. All right, several points to note. Okay.
It's a bit of lag.
Oh no!
So it's jumping around.
Come on, UCT. All right, several points to note. All right, so the structure constants themselves must satisfy a self-consistency relation. Due to the commutator satisfying the Jacobi identity. This is part of your homework. So we must have that C, D, B, C, C, E, A, D plus C, D, C, A, C, E, B, D plus C, D, A, B, C, E, C, D equals 0. I don't feel like this is particularly deep. It's just it's a true fact. All right, good. This is interesting. I've mentioned it before, but it's absolutely worth mentioning again. So while in physics, the natural Lie algebra object or objects are the Hermitian TA hats. The Lie group is a real manifold, right? That the parameters that describe any symmetry transformation are real. And so the manifold of parameters, which is the Lie group itself, is real. And so that tells me then that the Lie algebra, which is the vector space hanging out, which is comprised of the vector space hanging out in the tangent space of the Lie group around the identity, is itself real. using the TAs obscures this point. Oh gosh, sorry. Why does it obscure the point? It obscures the point because we said that the commutator, the Lie bracket, is I times some set of real numbers, and then the generators again. So you're like, oh, well, there's an I here, so obviously this algebra is complex. But that's not true, because by a simple scaling of my generators, I can make the algebra obviously real. So mathematically, it's more natural to work with, call them XAs, which we define as ITAs. Remember that when I expanded the unitary operator around the identity, I said 1 plus I theta A TA. And pulling that I out was exactly for this reason, that it emphasizes that those TAs are Hermitian. But as I said, it obscures the fact that the algebra is real, because if we work with these XAs, which are skew Hermitian, which says that if I take the Hermitian conjugate of these, I get minus themselves. So for physics, this is a super unnatural thing to work with. But then the algebra is given by XA, XB, Lie bracket equals C, AB, XC. With, again, just reminding you, these C's are all real, so this is obviously real. Okay. Why am I banging on about this? So the fact that the Lie algebras of interest are real is important, because we're going to complexify our algebra. If you remember yesterday, how did you construct the J plus minuses? You looked at a complex linear combination of J's. It's Jx plus minus I Jy. As soon as you've done that, you are no longer in the Lie algebra SU3. You're now in the Lie algebra SU3 complexified. Why is that okay? It's because of that statement that I made earlier, which I'm presumably going to say again in just a moment, which is that the representations of the complexified algebra of a real Lie algebra are in one-to-one correspondence with the representations of the original algebra. So long as we restrict the representations of the complexified algebra to the real part of that complexified algebra. Basically, what it means is, in practice, I have these e to the I theta A TAs. One way of thinking about complexifying the algebra is allowing for complex linear combinations of the TAs. An equivalent way of thinking about the complexification is allowing those theta A's to be complex rather than just real. And so the way to restrict the representations to the real part, the complex representations of the complex algebra, complexified algebra to the real algebra, is to take those representations, those complex representations of the complexified algebra, shove it into that exponential map, and only allow the theta A's to be real.
Yes, and that's what we want.
Exactly.
Okay, so we first complexify, work with the complexified, find the representation.
Yes.
And then.
Exactly. Precisely. My idea when I was writing these sets of notes was assuming that you had already done this whole process that you're going through in detail in the homework at least once. Okay, sorry. But hopefully now you kind of see a method to the madness. Why I'm asking you to go through in all this painful detail, these step-by-step instructions. All right, good. All right, good. I'm going to complexify our algebra by allowing complex linear combinations. Of the vectors in our algebra. And we complexify in order to obtain raising and lowering operators and we're by a theorem that tells us that the complex representations a real the algebra are in one-to-one correspondence with complex representations of the complexification of the real Lie algebra. So let me be specific. So some Lie algebra G and the complexification, which we denote by G sub complex numbers. Okay. Yeah.
Mathematically speaking, what is one-to-one response? Like I understand it intuitively.
It means that all of the representations that we're interested in finding, which are of our Lie group, can be found from the representations of the complexification of the Lie algebra.
You say found from, that what one-to-one correspondence is isomorphism.
It's not quite an isomorphism because you were losing something. You're losing this sort of, you have the ability to have the representation plus I and then the representation, and you're losing the I.
Yes.
But that's the only thing that you're losing. Good.
So those raising and lowering operators, those are like the TAs.
No, the TAs are the generators.
Oh,
The raising and those are going to be part of the real algebra. TA, TB is I, CABC, TC. You'll be doing things like what you've done, certainly in the homework and presumably in other contexts. You will be taking, for example, JX plus minus IJY. So the fact that you add vectors, add I hat plus J hat, that's fine. That's a real linear combination. I could do I hat plus 3 square root minus 1 J hat. So I hat plus 3 I J hat. That would be a complex linear combination of the vector space. I've complexified the vector space. Or I'm now allowing vectors over the complex numbers rather than just over the real numbers. And so what I'm doing is, what we are doing is we are going from the real Lie algebra, where we allow any real linear combination of vectors, any real combination of the generators, and we're abstracting, we're generalizing to allow now complex linear combinations. And so I will stop there for the moment. Yeah. Yes. Yes. Great. Yeah, absolutely.
But like in general, does this mean
Very good. So this procedure is completely general for any compact Lie group. Correct. Not necessarily. Now, if your position, so if you're thinking about position like on the real numbers, non-compact, then this is not going to be helpful for you. But suppose that you are a physicist in the mid to late 20th century, and people are building these particle accelerators, and they are spitting out all of these different particles. And what is a particle? A particle is some object that is a collection of properties that are invariant under something, basically the Poincare transformations. We are very familiar with the particle that we call the electron. What is an electron? It's an object that has a very specific mass, has a very specific charge, it's a very specific intrinsic angular momentum. And you can show from the method of induced representations, Poincare group being not compact, that the mass and the intrinsic angular momentum are the Casimirs of that group, p squared and the Pauli-Lubansky 4-vector squared, just saying the name so that you've heard it. That those quantities are not changed under a Poincare transformation for translations in time, space, rotations, or boosts. You know that p squared equals m squared always. It's also true for the intrinsic spin, intrinsic angular momentum. Okay, so you start with the mass and the angular momentum, but then you realize, oh, there's this other conserved quantity, which we call charge. Right, that no matter what I do, if I slam 2 electrons together, I might get a whole bunch of stuff out. But if I add up all that charge, I'm going to get 2e, no more, no less. So that's conserved. It turns out that there are other things that also seem to be conserved. Strangeness, for example. It was called strangeness because it was very strange that this emerged as some new quantum number. Famously said, who ordered that? All right. Well, now if you start trying to place order on this chaos of a huge number of particles, right? It's hard to put ourselves back into a place before we have our understanding of particle physics now, but all you have are these lists of masses, spins, and some kind of charges, where electric charge is familiar, but you have other charges that are unfamiliar. And you start trying to organize those in some way, especially in terms of masses. You have particles like, say, the electron and the positron, they have the same mass, but they have a different electric charge. But you think, oh, but that conserved charge is related in some way. And if you start doing this with respect to the strangeness, you again start to see an organization to the chaos. You've got your delta plus plus, your delta plus, your delta 0, I guess your delta minus, all have more or less having the same mass, different electric charges. You've got your proton and your neutron, basically the same mass, different charges. And if you are extraordinarily brilliant, you start trying to construct the unitary irreducible representations of SU3, because you see that the proton and the neutron live in the unitary irreducible representations of SU2, which we know and love. So if you start constructing those unitary irreducible representations, where now you have two Casimirs, and you have two different sets of raising and lowering operators, but you still have the theorem of highest weight. And so you can algorithmically generate these various representations, where now instead of with rotations, you have just a one line. So you can either have a point for the zero-dimensional representation, one-dimensional representation, 2 points for the two-dimensional representation, 3 points, so on and so forth. You now have an extra dimension where you can, the raising and lowering operators can move you in 2 dimensions now. And you see that these particles all fall in exactly these unitary irreducible representations of SU3, except for one of the very simple unitary irreducible representations where there's a missing particle. And you say, there should be a particle with this mass in this set of conserved charges that you should go and look for. And then that omega minus is found and you win the Nobel Prize. Yeah. So it is a completely general procedure, and it has, if the Nobel Prize is a decent metric for whether something is valuable or not, this is something that is very useful. I'm with you up until the discrete part. So any symmetry group that is compact, in fact, any symmetry, the unitary irreducible representations are going to tell us exactly what kind of quantities can be measured and what their values can be. And it can even go further than that, which we'll talk about a little bit later, which is that it will give very specific predictions for transition probabilities via what's known as the Wigner-Eckhart theorem, which you may or may not have seen in a particular example, which are the computation of the Clebsch-Gordon coefficients when you are coupling angular momentum. Yeah, that is continuous. Yeah, that's where you're not going to be using the theorem of highest weight, right? I think that that's going to be a true statement. I mean, because the thing is that, like, sort of, yeah, so it depends on what you mean by continuous. So if the quantity that can be observed is continuous, has a continuous spectrum, then you're not going to use raising and lowering operators. So for example, momentum, when you're thinking about momentum on the real, if you think about particles on the number line, so that's a non-compact group. Yeah. You could also ask, what do the raising and lowering operators? I thought what you're going to ask is what is the physical interpretation of the raising and lowering operators? And there, I don't think you can interpret them. I think it's purely a mathematical tool, because the real world is real, and as soon as we complexified our real algebra, what we're effectively doing is we're complexifying our manifold. We're going from thinking about the world in terms of x's to thinking about the world in terms of c's. And there, you know, at the end of the day, you're only going to measure real quantities. So the reason why we're complexifying is because of mathematical simplicity, not because of there being some physical consequence, at least not that I'm aware of. Yeah.
The process of defining and creating raising, you know, it works if you have like a maximum value.
Yeah, so that's the utility of these raising and lowering operators, is that you can rely on the theorem of highest weight, that there is a highest weight that does exist.
So like sort of like any imbalance system. If you want to create raising and lowering.
Only for compact Lie groups, yes.
Okay, well. So like for instance, the energy of an electron in an atom.
So the hydrogen atom is actually very interesting. I don't know the details, but there's actually a symmetry group of the hydrogen atom, which is SO4. And you could presumably then compute the unitary Urs representations of SO4. That will tell you probably everything that you would ever want to know. There are books that have done this. I've quote unquote read them at some point. In a land of infinite time, I would go back and read them again.
Okay, but like theoretically, you would have raising and lowering operators for quantities.
Yeah.
In that system, but not the electrons.
Correct. In free space, then your symmetry group is Poincare, as Tian mentioned. That's a non-compact group. And non-compact groups are bad juju because they're, by math, the only unitary representations are infinite. Yeah. It's a blessing and a curse for reasons that let's not get into today. Good. I feel like these are all very good questions. I feel like we're learning. Any more questions before we continue along this path? Okay, super. So what are we up to? Oh, this is okay, 2, 3. These CABs, the CAB are necessarily antisymmetric. And they're lower indices. So we have that CCAB is necessarily going to minus CCBA, but aren't necessarily totally antisymmetric. Remember that for your generators of rotations in SO3, you found that those structural constants were totally antisymmetric. It was Ji, Jj's, I, epsilon, ijk, jk. But that is because SON is what's known as a semi-simple Lie algebra. And for semi-simple Lie algebras, you can find a basis for which these structural constants are totally antisymmetric. But that's not necessarily generally true. However, the semi-simple Lie algebras include SON, SUN, SON1, SLNC for n greater than 1. So basically, all of the Lie groups that we care about, their Lie algebras are going to be semi-simple. And so the structural constants can be found to be totally antisymmetric. But just as a sort of a minor aside, that's not necessarily always true for all Lie algebras. Okay, good. So if we have a map associated with a representation, which is taking elements of our group into our GLNCs. So not just the general linear group on some vector space, rather into the set of, or the group, the Lie group of n by n matrices with complex entries that have non-zero determinants. Basically, the maps that we're generally interested in. If this is a group homomorphism, which is to say that is the map associated with a representation, then the map, which I'm going to call pi hat prime, which takes elements from the Lie algebra of our Lie group into the Lie algebra, these n by n matrices with complex coefficients with non-zero determinant, which we define by the derivative of our map of the exponential map around the identity. So I'm taking the exponential map where my TB lives in the Lie algebra. And so this object lives in the Lie group. And I'm asking for the operator associated with that element of the Lie group. I'm expanding around the identity and looking at the linear term. And I'm defining that as this pi prime, kind of like a derivative. Then this pi prime is a group homomorphism itself that satisfies first that of e to the I theta a ta is equal to e to the I theta a pi hat prime ta. And this is really everything that we're going to be leaning on, right? When I talked about this commutative diagram that's taking me from G to GLV and then up to my algebra G and then the algebra GLV over here and then back down again. This is the map pi prime and this is the map pi. I care about pi, but I'm using my pi prime map. And I'm guaranteed by this math that I claim without proof that I'm able to do that systematically. So what you work through in the homework is these pi prime maps, which then give you the pi maps relationship. Okay, good. And secondly, the pi prime respects the algebra. So pi hat prime preserves the algebraic structure of the group, or of the algebra rather. Well, these things are synonymous. Okay, good. This is what I wanted to cover in terms of Lie algebras. So let me pause here. Last chance. Okay, let's talk about projective representation. Okay. For our example of SO2 isomorphic to U1, we found the ordinary finite dimensional unitary irreducible representations are these UMs of theta. So the group is parameterized by theta. So group element is given by theta. The map, which takes us to an operator, is unitary, so I call it U. And it is classified by the value M. So if M is 0, that's 1. representation. If m is 1, I have another representation. If m is -5, I have yet another representation. These things are equal to the e to the I theta m, where m is an element of z. Notice that my pi prime hat m of j is equal to m. Or I could call this perhaps, since it's unitary, the u hat prime, because the u hat map is unitary. Okay, so what does this mean physically for the experimentalists in the room and for the theorists who care about the real world? So physically, orbital angular momentum is quantized. Orbital angular momentum in the plane, in the 2D plane, is quantized. So that orbital angular momentum, L, is an element of Z. So if I have, I guess I should say, yeah, so if I have a physical setup where I have symmetry, rotational symmetry in 2 dimensions, I know my orbital angular momentum is quantized. For someone who has done quantum mechanics in first-year physics, with the first introduction to ideas of quantum mechanics, and you've done maybe 2 different quantum mechanics modules in undergrad, it's probably old hat for you that things are quantized. But maybe try to put yourself back in that place of innocence before you were introduced to quantum mechanics, where almost everything that you experience in the real world is continuous. And so it's actually wild that just the fundamental postulates of quantum mechanics lead us directly to a discrete nature of some observable quantity in the real world, that quantity cannot have non-integer values at all. Okay, so if the theta were the only possible UIRs for SO2 isomorphic to U1, then the intrinsic spin of particles in a symmetric 2D space would be quantized with allowed values also only integers. But did we miss any representations? And the answer is yes, leading question. Recall that projective representations or representations up to a phase I don't know why. This is very late night when I was writing these notes, so I'm apparently not making complete sentences. So recall the projective representation up to a phase must be allowed in quantum mechanics, since quantum mechanics is insensitive to phase. So we must allow for pi hats of G such that if, so G 2, 3 are in our group, with G1 followed by G2 gives me G3 in the group multiplication law. Such that if this, then pi hat of G1 followed by G2 gives me e to the I, some real number that can depend on both G1 and G2 pi hat G3. So groups can have what are known as intrinsically projective representations. In two cases. So one, the Lie algebra can have what are known as central charges. In which case, even the representations near the identity can be projective. Or two, the Lie group can be topologically non-trivial. And we're going to focus on two. We're going to focus on two because the rotation group, so SON, the SUN, the SON1, the Poincare group, all of these, or rather none of these have central charges, which is just an additional complication. It's hard, life is hard enough as it is. So let's focus only on the topologically non-trivial ones. In principle, especially in non-relativistic quantum mechanics, we should think about central charges, because the Galilean group, in fact, has central charges. So the group of symmetries, space-time symmetries for non-relativistic physics has central charges. We're not going to talk about that certainly at this point. Yes. Good. I'm intentionally not telling you what that is, because we're not going to worry about it. But because you asked, remember that the commutation relation for generators is the definition of a central charge is when you have your commutator has some part or some contribution which is proportional to the identity. So for SO3, we have Ji, Jj is I epsilon ijk, jk. If there were a central charge, it would be plus that, it would be I epsilon ijk, jk plus 1 times a thing, where that 1 is the identity element in the vector space. For the Galilean group, the central charge ends up being the mass, for example. Yeah, let me stop there. Yes.
What is the definition of topological reality?
We'll get there. Good question. All right, good. Good. So I will get there not immediately. I'm going to say a bunch of more words that are going to necessarily need to be defined, but we actually did it yesterday informally, but I'm going to do it formally today. And that should give you a clear answer to your question of what does topological non-triviality. Good. So we'll focus on 2 in this course. Good. And the following theorems will be helpful. So all representations of a group G are representations of G twiddle, the universal cover of G. I'll define universal cover in just a moment. All finite dimensional continuous representation of a simply connected group G twiddle are ordinary. I'll define simply connected in a moment, formally. If G twiddle is simply connected, then there's a one-to-one correspondence between the group representations and the algebra representations. Okay. So a space is simply connected if all closed paths can be continuously contracted to a point. And we talked about this, I think, informally at the start of today's lecture. We talked about it formally yesterday. So I think that you have a good grasp on simply connectedness, but let me pause to see if there are any further questions now on simply connectedness. It is an important concept, at least conceptually, for what we're doing. Yes. I'm not going to do that. Yeah, so you can formally define paths in terms of one parameter curves living in the thing, and then what a continuous deformation is. I don't want to go into that detail. I don't see that as important for us. Yeah, I think at the level of a relatively sophisticated conceptual understanding is sufficient for us. Yes.
What is the space? I mean, like.
Yeah, so an example of a space would be a manifold, but a space is more general than a manifold. So collection of items, call it.
Okay, so
there's got to be more structure on it than that, but yeah.
Okay, so it's more than a set, less than.
Yes. Good. No, that's a fair question. Yeah. Presumably you have to have some ability to do sort of calculus-y things because you have to have a notion of continuity. So you must have some, because you must have to have a topology on there. Good. Other questions? All right. Good. So a group G is a cover of group H if there exists some projection map which takes us from G to H such that this P mapping is a group homomorphism. So what I think is sort of a useful visual is, suppose I have it's meant to close up. So I have my group H here, and I think about some group G, which is, maybe some things that look like this. And I use my map P to project down where P preserves the group structures. Okay, and G twiddle is a universal cover of G if G twiddle is a cover and is simply connected. Good. And this is important. The universal cover of a connected group is unique up to isomorphism. So thus the universal cover of a connected G is the group G twiddle with the same Lie algebra so the Lie algebra G is isomorphic to the Lie algebra G twiddle and is simply connected. So here's our overall plan. We want to classify the possibly projective unitary irreducible representations of our symmetry, which is to say Lie group, call it G, and we want these unitary maps, which are functions of the group elements. We parameterize the group in terms of some kinds of parameters. And so if we give some parameters to our map, it spits out some operator operating on some complex vector space. And different representations are classified by some set of numbers. So for example, for rotations in 2 dimensions, it's just one number, which is the spin. Similarly for rotations in 3D, again, there's just one number, which is the spin. If you are thinking about the Poincare group, well, if we think about, say, the connected component of the Lorentz group, then there are 2 numbers, a J1 and a J2. Those uniquely identify the different representations of the Lorentz group. Okay, good. So some set of numbers that tells us what representation we are in. If our group G is not simply connected, then these U hats may be projected. So if the G is not simply connected, so if G isn't simply connected, we rather consider the ordinary UIRs of the universal cover of G. Which I'll call G twiddle. And these are the U twiddle hats, again, of the lambda mu's of theta A's. Okay. Yes.
Universe, U lambda, what is that a mu?
Yes, so indicate that there's a collection of numbers. So I called it a mu, Yeah. I mean, maybe in the spirit of I have a theta and then an A, maybe I should have a lambda and then an M. But I'll leave it as a mu just for my own self-consistency. Okay, good. So since this G twiddle is the universal cover, there exists some projection P, which is going from the G twiddles to the G, which is taking the parameters in the universal cover into the parameters of the original group. And we introduce one more map, which we call S, which goes from our group to the universal cover, which takes our theta A's to our theta twiddle A's. Defined such that the projection of the section of the parameters gives us back the parameters. Yes.
Sorry, did you say S is called a section?
Yes, in terms of topology, it's known as a section. You can talk about base spaces and fibers and fiber bundles. If that gives you deeper insight into what we're doing, that's amazing. If it doesn't, don't worry about it. We don't need it in any way whatsoever. But I labeled it an S because it is a section, technically a section. Okay. Then the things that we're interested in, these unitary irreducible representations of our group elements, which are denoted by the parameters theta A, these are given by the unitary irreducible representations of our universal cover. Now, the universal cover doesn't have the parameters living in the group, right? The parameters of the universal cover live in the universal cover. So we need some map that's going to take us from our parameters of our group to our parameters of the cover, and that's the section. That's precisely the section. So I take the parameters from our group into the parameters of the universal cover. Then these U lambdas are precisely the UIRs we see for our group G. And so the point is, from a pragmatic perspective, we actually only end up working with the representations of the universal cover. So for example, for rotations, we started with SO3. We say, cool, we want to know what possible states we can have in SO3. We'd like to understand how to effect a rotation in 3 dimensions on our Hilbert space, because that's something I can do in the real world with an experimental apparatus. I'd like to be able to make predictions for that procedure. And so I say I would like the unitary irreducible representations of the SO3 group, but we recognize that that group is not simply connected. And so I end up finding the unitary irreducible representations of SU2, the universal cover of SO3. I end up just working with those. Having said that for SO3, oh, actually, I have a note to myself in terms of providing an even deeper understanding, where these are just words that I want you to hear. And if you never hear them again in your life, that's fine. But it's a beautiful mathematics if you want to get into it, and it provides really a deep understanding of what's happening. And that's that that the universal cover is actually what's known as a central extension of our original group by its fundamental group. The fundamental group is a algebraic topological object, which tells us about the connected or the extent to which our group or our manifold deviates away from simply connectedness. And there is what's known as a short exact sequence, is going from the fundamental group to the universal cover to the group itself, which is the universal cover quotiented out by the fundamental group. Again, these are very deep connections between group theory and topology. And as mentioned, so the group G is the base space, the fundamental group is the fiber, and the universal cover is the fiber bundle. Okay. So totally fine, but words that I would like to have all of you to have heard at least once in your life. And for people who are going to continue on sort of a more theoretical perspective, you will see those words again. So I just want you to sort of have in your mind, like, oh, fibers, that's actually has a connection to the representation theory that I used in quantum mechanics. That was my goal for those statements. Okay, coming back to things that I do think are valuable for you and useful for you, and that you will be tested on at some point. Let's see how all this works, specifically for rotations in 2 dimensions. Well, okay, so it's almost 11. I could stop and we could do the specific example on Monday. I don't know that you necessarily need to see the specific example for the homework. I honestly don't remember. I feel like I'm on a roll and we could keep going, but do you want to call it quits, or do you want to? I have 2 more pages. You want to call it?
Yeah.
Not a problem. All right.
But maybe
Yeah, well, you know what? Let me just upload the full set of those notes, and then we'll go through them in detail. Yeah. Will you look up fiber bundles? Yeah.
no. One day.
Maybe. All right. Before I stop recording, any last questions, comments, thoughts? For the record, did you enjoy this?
I thought it was well made. The beginning was quite rushed. I mean, it felt rushed to me because we were working on those that but then once you started writing, I was like much more concentrated.
Couldn't we have just stopped the recording before you added the constructive criticism? So again, how was this lecture?
Great.
Best thing you've ever heard, right? Okay, I'll stop. All right.